Now we are going to start the new chapter, chapter number 7, alternating current. You know what is alternating current? AC. That means the current whose magnitude changes continuously with time and the direction changes periodically or direction reverses periodically. So if a graph is plotted, time along the x-axis, voltage or current along the y-axis, here this represents AC voltage or AC current. Here the magnitude changes continuously with the time. Here magnitude is 0, then goes on increasing, it becomes maximum, then it goes on decreasing, it becomes 0, then it reverses the direction and increases. Again on the other region it becomes maximum, again it becomes 0. So its magnitude changes continuously with the time and the direction changes periodically. At this time interval, what happens? The direction reverse. So this is the representation of AC voltage or AC current. The direction changes periodically and the magnitude changes continuously with time. So this is the representation of AC. Now how will you represent a DC voltage? DC voltage means the voltage always remains constant. The magnitude of voltage remains constant. So this is the representation of DC. The voltage, if it remains constant, so this is called a DC voltage or DC current. This is DC. So AC means the magnitude changes continuously with the time and the direction changes periodically. DC means the voltage or magnitude of the current and voltage remains constant throughout. That is called a DC. Here in the chapter, we are confining our studies on alternating current. What happens if AC voltage is given to different electrical devices like resistors, capacitors, inductors, etc. Today most of the electrical devices we use require AC voltage. This is mainly because most of the electrical energy stored by power companies is transmitted and distributed as AC current. The main advantage of AC over DC is it can be easily and efficiently converted from one form or one voltage to another by means of transformers. So using transformers, AC voltage can be transmitted over long distance. And further electrical energy can also be transmitted economically over long distance, and hence most of the electrical devices are based on AC. In the last chapter we have studied how will you represent an AC voltage. What is the output of an AC generator? Output of an AC generator is represented in that chapter. AC voltage was represented as E equal to E0 sin omega t. Here in this chapter we can represent AC voltage as AC voltage is usually represented as AC voltage can be represented as V equals Vm sin omega t. This is the representation of AC voltage. V represents the AC voltage, Vm represents the peak value or the maximum value. Peak value means this represents the peak value. Here this is the peak value. This is called the peak value which is represented by Vm. Here it is minus Vm. So this represents the maximum value or the peak value, or it is also called the amplitude. Now omega t, what is this omega t called? Omega t is called phase. Omega t represents the phase and omega is called the angular frequency. So Vm is the peak value, omega t is called phase, omega t is called phase and omega is called angular frequency. Study the first one, AC voltage connected to a resistor. What happens when AC source is applied to or it is connected to a resistor R? So this is a representation of AC source. This is AC source. If that AC source is connected to resistor, now they produces a current I, AC current I. AC current is usually represented as small letter I. So I be the AC current flowing through the resistor. We have AC voltage. AC voltage is given by V equal to Vm sin omega t, where Vm represents the peak value, omega t represents the phase. Either we can use Vm or V0 is also used. So AC voltage is given by V equal to Vm sin omega t. Now what is the current flowing through the resistor? I be the current flowing through the resistor. So from Ohm's law, the voltage across resistor can be written as voltage across the resistor R can be written as V equal to IR. Okay, so AC voltage is Vm sin omega t, voltage across the resistor R equal to IR. So using these two we can write Vm sin omega t is equal to IR, equating, or current I can be written as Vm divided by R sin omega t. So I equal to Vm divided by R sin omega t. What is this voltage by resistance? Peak value of voltage by resistance is current. So Vm divided by R equal to the current Im, the peak value of current Im. And hence we can write current I equal to Im sin omega t. So when AC voltage is connected to a resistor, voltage is Vm sin omega t and the current is I equal to Im sin omega t. Okay. What about the phase here? In the voltage, phase is omega t, current phase is also omega t. That means voltage and current have the same phase. So when AC voltage is connected to a resistor, voltage and current are in phase with each other. Here voltage and current are in phase with each other. Okay, next, instantaneous power dissipated in a resistor. We have the power given by the formula I square R. Okay, what is I? I equal to, we have derived I as Im sin omega t the whole square into R. Okay, so it is equal to Im square sin square omega t into R, or instantaneous power can be written as Im square R sin square omega t. This is the formula for instantaneous power. Okay. So instantaneous power dissipated in a resistor is P equal to Im square R sin square omega t. Now we can derive the formula for average power. Average power. Average power means it is the power dissipated for one complete cycle of AC. This is called the average power. So average power is power dissipated for one complete cycle of AC. Okay, and average power is usually represented by P average. So this is the representation of average power. And how will you find out the average power? P average is given by, we have to take the instantaneous power and we have to take the average. So this represents average of the value taken inside. Okay, we have to find out the average of the right side. What is in the right side? Im square R sin square omega t. So this is the method of taking average of the quantity. Okay. Now Im square and R are constants. So average power can be written as Im square R into, we have to take the average of sin square omega t. And average of sin square omega t is half. So average of sin square omega t is equal to 1 by 2. That is from the trigonometry. So average of sin square omega t is 1 by 2 and hence the average power is given by Im square R divided by 2. So average power is given by P average equal to Im square R divided by 2, where Im represents the peak value, R represents the resistance. So this is the formula for average power, that is power dissipated for one complete cycle of AC. Now, so we have derived the formula for average power as Im square R divided by 2. But in DC, the power dissipation, for DC, power is given by, in DC there is no average power or the peak power. Okay, there is only one power in the case of DC, because current always remains constant in the case of a DC. Therefore, power dissipated for DC current is given by I square R. For DC, power dissipation is given by I square R. But for AC, average power dissipation is given by Im square R divided by 2. So to express AC power in the same form as DC power, a special value of current is defined and it is used also. And that special value of current is called root mean square current, or it is called effective current. So what is the importance of root mean square current or RMS current or effective current? To express the AC power in the same form as DC power. DC power is I square R and average AC power is given by Im square R divided by 2. So to express AC power in the same form as DC power, a special value of current and special value of voltage is also there. Special value of current or special value of voltage is defined and used, and that value is called effective current or RMS current, that is root mean square current. So to express AC power in the same form as DC power, a special value of current is defined and used, which is called root mean square or RMS or effective current. It is represented as IRMS. And what is the value of IRMS? IRMS is given by Im divided by root 2. This is the formula for RMS value of current. IRMS is given by, it is root mean square current, and it is given by Im divided by root 2. Similarly, RMS value of voltage is given by Vrms is equal to Vm divided by root 2. So Vm and Im represents the peak value of voltage and current, and Vrms and IRMS represents RMS value voltage and current. So the relation between RMS value and the peak value is IRMS is equal to Im by root 2 and Vrms is equal to Vm divided by root 2. Now we can represent here, we have average power given by, average power is given by Im square R divided by 2, isn't it? So average power can be written as, what is this Im? Im equal to IRMS into root 2 the whole square. We can substitute, isn't it? Divided by 2. Substitute for Im equal to IRMS into root 2. We have, if you want to take the square into R divided by 2. Here 2 and 2 get cancelled. So average power is IRMS square into R. So we got the formula for power, average power in the same form as DC. For DC, the power is given by I square R, and for AC, the average power is given by, what is the average power? IRMS square into R. Okay, children? So that is the importance of RMS value of current and RMS value of voltage. Similarly, we have another formula for power. What is another formula for power? We have the power P equal to V square divided by R. So here it is Vrms square divided by R. Similarly, one more formula, average power is also given by P equal to Vi. Okay, power is also given by another formula Vi. In AC, average power is given by Vrms into IRMS. Clear? So for AC, almost all current and voltages are expressed in terms of RMS value of current and RMS value of voltages. Okay. Now we know that in an AC, a voltage connected to a resistor, voltage and current are in phase. Okay, so we have for AC voltage connected to a resistor, voltage is equal to Vm sin omega t, and current I equal to, what is the current I? Im sin omega t, that you know. And what is the value of Im? Im equal to Vm divided by R. Okay. Now, how will you draw the graphical representation of voltage and current? Here, graph is plotted with omega t is plotted along the x-axis. The phase omega t is plotted along the x-axis, and in the y-axis voltage or current. Voltage and current. Voltage and current are plotted along the y-axis. Okay. Now, here, how will you represent the voltage? Voltage is represented like this. This represents the voltage. Okay, so from 0, here this represents the maximum value is pi by 2. Here this value is pi, middle value is 3 pi by 2, and this value is 2 pi. Okay, Graph is plotted for a one complete AC, 0, pi by 2 pi, 3 pi by 2, 2 pi. In degree we can write 90 degree, here this is 180 degree, this is 273 degree, 270 degree and this is 360 degree. Okay, that is angle. So this represents voltage. So solid line represents voltage. Now how will you represent the current? Here voltage and current are in phase because here omega t for current also same phase. Voltage and current are in phase. But what about the magnitude of current? Im equal to Vm by R. So magnitude of current is less than the magnitude of voltage because Im equal to Vm by R, current magnitude is less or the amplitude of current is less. But voltage and current are in phase. So how will you represent the graph representing current? So here the same phase, therefore it passes through the same point but its magnitude is less than voltage. So this is the graph representing current. Okay children, because voltage and current are in phase, therefore they pass through the same points and the current magnitude is less than voltage magnitude. So here this represents current. So dotted line represents current. And here this value, the maximum value, the peak value, this is the peak value and this corresponds to, what is this corresponds to? Vm. And here this corresponds to Im. So this is the graphical representation of voltage and current when AC voltage is connected to resistor. From the graphical representation it is clear that voltage and current are in phase. Okay, now we can discuss what are phasors and phasor diagram. So phasor means in order to show the relationship between voltage and current we use the notion of phasor. Phasor is a vector which rotates about the origin. So normally voltage and current are considered to be scalar, but in AC voltage and current can be considered to be vectors because here the voltage is continuously varying, periodically changes its direction, isn't it? So in one case it becomes positive and another case becomes negative. So here in AC voltage changes periodically with the time and it reverses its direction also. And hence in AC voltages, AC voltage and AC current can be considered as a vector. Phasor means it is a vector which rotates about the origin with angular speed omega. And the diagram which represents AC voltage and current as rotating vectors or phasor is called a phasor diagram. Okay children, so what are phasors? Phasors are a vector which rotates about the origin with an angular speed omega and the diagram representing AC voltage and AC current as phasors, and that diagram is called a phasor diagram. So using the phasor diagram we can easily identify the relationship between voltage and current similar to this graph. From the graph we can say that voltage and current are in phase or out of phase. Similarly using the phasor diagram we can identify, we can find out whether the voltage and current are in phase or out of phase. Now how will you draw the phasor for an AC voltage connected to a resistor? So this is the graph already we have discussed. In an AC voltage connected to a resistor, voltage and current are in phase. So if a graph is plotted with omega t along the x-axis, voltage and current along the y-axis, this is the graph. Okay, this line represents, solid line represents voltage and the dotted curve represents current. Since they are in phase, they pass through the same point. And the magnitude of current is less than the magnitude of voltage. Now, how will you draw the phasor? Phasor is drawn if you consider an angle between 0 and pi by 2. This maximum value is pi by 2. If you consider an angle between 0 and pi by 2, let that angle be omega t1. Okay, consider an angle between 0 and pi by 2, let that angle be omega t1. From that omega t1, draw a perpendicular like this. Okay, so here it touches the voltage curve and here it touches the current curve. From that, draw a perpendicular here. Okay children, so from that draw a perpendicular like this. And here it touches the current curve, from that again draw a perpendicular. Okay, so here it touches the voltage curve, from that draw a perpendicular. Here we can draw the phasor. This is the graphical representation and here on the left side we can draw the phasor diagram. So consider an angle between 0 and pi by 2. Let that angle be omega t1. From that, draw a perpendicular so that it touches the voltage curve and the current curve. From that point, draw a perpendicular like this. Here also draw a perpendicular. Now from the origin, this is the origin. From the origin, draw a vector. So this vector represents, this is the voltage from the voltage curve, no? So this represents voltage phasor. Here this represents the current phasor. So here bigger one represents a voltage phasor and the smaller vector represents the current phasor. What does it mean? Voltage and current are in phase. So therefore the line is same. Since voltage and current are in phase, so this represents the phasor diagram when AC voltage is connected to a resistor. Okay, now what is this value? This angle is omega t1. So it makes with the x-axis is omega t1. And what is its magnitude? This magnitude is Vm and this magnitude is Im. The magnitude of voltage is greater than the magnitude of current. And the line drawn from the phasor towards the x-axis, this is called a projection. A line drawn from the voltage phasor towards the x-axis, this is called a projection, and this projection is actually Vm sin omega t1. And this projection is, what is this projection? This is Im sin omega t1. So projection of voltage and current phasor is Vm sin omega t1, and here this is Im sin omega t1. So from the phasor diagram we can clearly say that voltage and current are in phase because same line. Okay, so voltage magnitude is greater than the current magnitude and the projection is Vm sin omega t1 and the current projection is Im sin omega t1. So this is the phasor diagram of AC voltage connected to a resistor. So once more, first draw the graphical representation. Consider an angle between 0 and pi by 2. Let that angle be any angle omega t1. From that, draw a perpendicular and draw lines like this. Here from the origin, draw a vector. That vector represents the voltage phasor. Here this line represents a current phasor. Since voltage and current are in phase, they pass through the same line. And the angle is omega t1. So this is the phasor diagram of AC voltage connected to a resistor. In resistor, when AC voltage is connected to a resistor, first we have studied AC voltage is connected to a resistor, voltage and current are in phase. That is the first thing. Now next we have derived the formula for instantaneous power, next average power, then graphical representation and phasor representation. So these are the properties we have to study in each case. First we have to draw the circuit, now derive the formula for current, derive the formula for instantaneous power, then average power, draw the graphical representation and phasor representation. Okay, next class we have to study what happens when AC voltage is connected to a inductor, capacitor, etc. Okay children.